Okay, welcome back everyone. What we're going to do here is continue on with our discussion of Ampere's law. We've introduced it, we've seen one really simple example where we can use Ampere's law, and that's a infinitely long thin wire. Now what we're going to do is take this a step further and do several different examples where we can use Ampere's law, and the next one is a wire with a uniform current density. So here's what the problem says. We have an infinitely long conducting wire of radius r, which has a current such that the current density is uniform. So remember what current density means. This is given by J. It's di dA, so the current per unit area in the wire. That's going to be uniform. So what we're going to do is use Ampere's law to find an expression for the magnetic field as a function of r, distance from the center of the wire. So the section of the wire is shown here in the diagram below. You see the current going through it. Of course, we're only seeing a small portion of the overall thing. It's infinitely long. And what we're going to start with is applying Ampere's law to loop number 1, where the radius of that loop is less than the radius of the wire. So little r, which is the radius of the loop, is less than big R, which is the radius of the wire. So we're talking about inside of the wire. Okay, so we'll work out what the magnetic field looks like there using Ampere's law. Let's go into that.
All right, so this is what's going on. We have a wire. The radius of that wire is r, so that's shown right here. And we're looking face on into the wire. That's the perspective we're taking in this picture. Now we have an Amperian loop that we're drawing in order to solve the problem. And that has a radius which is smaller than the radius of the wire. So there's little r for our loop, and that's shown with a dashed line right here. Now, dl represents a little bit of this path that we take when we complete this entire loop. Okay, so with that said, we're using Ampere's law. B dot dl equals mu naught times I enclosed. So for now, I want you to imagine that the current is, let's say it's coming out of the page. So there's I for this wire. We're not enclosing the entire current with this loop. In fact, we're only enclosing a portion of it, right? And the way we want to conceptualize this is whatever fraction of the total area that we're enclosing with this loop, we're enclosing that same fraction of the total current. So in other words, if this encloses 50% of the total area, then it should also enclose 50% of the total current, right? Because the current is just uniformly spread out across that area. That's what it means to have a uniform current density. Okay, because J is uniform, current density is uniform. Because of that, we can state that I enclosed divided by I total is equal to the area enclosed divided by area total. Okay, so I enclosed is something we want to know, we want to solve for it, so let's leave that right here. Okay, I total, well that's just I, and the area we're enclosing is a circular area where the radius is lowercase r. So we have pi times little r squared up here. A total is the area of this entire wire. That's the full cross-sectional area of it. So pi times big R squared is going to give us that area. So of course we can cancel out the pi's, and we get that I enclosed is equal to the current running through this wire times little r squared divided by big R squared. So in Ampere's law, we've accounted for the right-hand side. Okay, so we're going to plug that in when the time comes, but we still have to deal with this B dot dl thing. We have to figure out what that is. Okay, so B dot dl. First, if the current in this wire is coming out of the page like this, okay, our magnetic field, we can find it through the right-hand rule which way it's going. Okay, my thumb is in the direction of the current going out of the page, and my fingers on my right hand are now curling in the direction of the magnetic field. So I'm not going to draw a whole loop. We know the magnetic field lines are kind of looping around the entire wire like this, But I'll just show a little bit of one of those lines. There's B right there. Again, looping around like this, going counterclockwise. So the B field in DL are going in the same exact direction. You can just see that from the diagram, which means when we take the dot product, we have the magnitude of B, the magnitude of DL, and then cosine of 0. Cosine of 0 gives you 1. And then the next thing to see here is that the B field, in terms of its magnitude, it's actually uniform all along this loop, because all along this loop we're staying the same distance from the center. So what we'll do is we'll pull out that B as a constant, because it's, again, constant over our loop, and then we'll have integral of DL cosine of 0 goes to 1. So this is just saying to add up all the little distances along the path here until we've covered the whole thing. Well, this path is a circle, so the total distance around the circle is 2 pi r, the circumference. So we have magnitude B, and then we have 2 pi r. That's how this works. Okay, so the last thing is just to put these two pieces together using Ampere's law. We know B dot dl, we know I enclosed, so let's plug them in and see what we get. So on the left side we have magnitude B times 2 pi r. On the right hand side we have mu naught times I enclosed, which is I times little r squared over big R squared. So what we're interested in is solving for the magnetic field B. So what we have is on top mu naught times I. Now if we divide out this R right here, we're just going to have one factor of R on top. So we cancel with one of the factors in the R squared. And on the bottom, we're going to have 2 pi and big R squared. Okay, so that's a good formula for the magnetic field inside of a wire, as long as that wire carries a uniform current density. That's what this is.
Okay, so the result is that the strength of the magnetic field inside of the wire is equal to mu naught times I times little r divided by 2 pi times big R squared. So notice how everything here is a constant except for little r. So this is just telling us that the magnetic field is increasing linearly as radius increases when you're inside the wire. So the magnetic field gets stronger and stronger as you go out from the center of the wire. So the next thing we want to do is, if we want to understand what the magnetic field looks like outside of the wire, we'll put another Amperian loop. This time the radius little r of that loop is bigger than capital R, which is the radius of the wire, so we're outside now. And again, we're just going to apply Ampere's law and solve for the magnetic field outside of the wire. So let's work that out.
Okay, and now to figure out what the magnetic field looks like when we're outside of the wire. Here, our Amperian loop is similar to before. It's a circle that goes around the wire, but now our circle is just outside. So there's my DL vector, just a little piece of this overall path. And there's my radius little r. There's the radius of the wire as before. So we have the current coming out of the page. So just like before, we're looking into the wire. And we know from the right-hand rule that our magnetic field lines are going like this, which is counterclockwise. Okay, so we're using Ampere's law. B dot dl is equal to mu naught times I enclosed to figure out what this magnetic field is. And the nice thing is that I enclosed is super easy to think about. Since we're not inside of the wire and only partially enclosing the current, we're outside of the wire, so we're enclosing all of it. So I enclosed is just the total current in that wire, so that's I. And another nice thing is that for B dot dl, we already know what this looks like, okay? We know that when you have your B field lines going in the same direction as the loop, and that's a circular loop like this, that B dot dl just works out to magnitude B times 2 pi r. Okay, so we already went through why that works out. So all we need to do then is put it together. In Ampere's law, we have the magnitude B times 2 pi r for our integral, and then we have mu naught times I on the other side. So the magnitude of B is mu naught times I divided by 2 pi r. So that's what the magnetic field looks like outside.
And the result is the strength of this magnetic field is equal to mu naught times I divided by 2 pi r. And you might notice that just looks like an infinitely thin wire as long as we're outside. So that's the result. We have the result for inside the wire and outside the wire, what the magnetic field looks like. So the next thing we'll do is kind of plot this out. Okay? If you think about the magnetic field, it's this sort of piecewise function where, again, for values less than big R, we have a certain result, and for values bigger than that, we have another result. So when we're inside the wire, as I said earlier, the B field increases linearly as we go out. So if we plot it, B as a function of R, so B is on the vertical axis and R is on the horizontal axis, that should just look like a straight line. However, if we look at what's going on when we're outside of the wire, it looks like B is inversely proportional to R because little r is now on the bottom. So the B field strength is decreasing with distance. It's getting smaller, it's getting weaker as you increase the distance, like 1 over r. So we draw that curve, and that's overall what the magnetic field looks like. It's right here on the graph. So increasing linearly inside the wire, falling off as 1 over r outside of the wire. Okay, so here's the question for the class. In this one, you have to make a few calculations. Let's say we have a long straight copper wire with a diameter of 2.10 millimeters, and that wire is carrying a uniform current density of 6.75 times 10 to the 5 amps per meter squared. So we're not given the current here, we're actually given the current density. So the first question is, what is the magnetic field 0.5 millimeters from the center of the wire? The second question is, what is the magnetic field 4.5 millimeters from the center of the wire? Okay, so we're going to use the expressions that we derived just a second ago for, again, a wire that has a uniform current density inside of it. And that expression is given on the bottom of the page. One thing that goes into this is the permeability of free space, that constant mu naught, that's also given to us. So with all these numbers and the expression that we derived, you should be able to figure out how strong the B field is at these different locations. So go ahead and try to work this out. Pause the video and then come back to it and see what the solution is.
Okay, so our first move here is to find the current that's going through the wire. What we're given is the current density. So let's just remind ourselves what current density is. It's given by the variable J. It's the current per unit area. So it's I divided by A. Meaning if I want to know what the current is, I is equal to J times A. We have to think about what the area is in this context. So the assumption for a wire is that it has a cylindrical shape. And the cross-sectional area that the current is moving through is a circle. It's a circular area. So A for a circle is pi r squared. So now we have J times pi r squared. If we can calculate this, then we'll know what the current is. So let's do that over here. The current is J. Our current density that was given is 6.75 10 to the 5th amps per meter squared. And we multiply by pi. The diameter of the wire was given to be 2.1 millimeters. So the radius is half the diameter. 2.1 millimeters is 10 to the minus 3 meters. And we'll square that. This gives us the current. This works out to about 2.338. Units are amps. We'll round that off to a nice 2.34 amps. So that's how much current in the wire we have. Okay, the next thing is, let's find the magnetic field when the radius is 0.5 millimeters. So we're gonna figure out how strong the magnetic field is 0.5 millimeters away from the center of the wire. Okay? So in this case, little r is equal to 0.50 millimeters. And we have to recognize that we're inside of the wire, okay? So in other words, we're in the situation where little r is less than big R, we're inside the wire, okay? Let's actually write that down. So we're inside the wire. Which means the formula for magnetic field that we're going to use is this one. It's mu naught times I times little r divided by 2 pi times big R squared. That's what we need to calculate. Well, in this case, what we have for mu naught is 4 pi 10 to the minus 7. And for the current, we have 2.338. Okay, for the distance from the center, we have 0.5 millimeters, 0.5 10 to the minus 3 meters. I'm leaving off the units here just because I'm running out of space. And then we'll divide that by 2 pi times the radius of the wire squared. The radius of the wire, as we said before, is half its diameter, half of 2.10 10 to the minus 3, and we have to square that. Okay, so when you make this calculation, you end up getting 2.12 10 to the minus 4 Tesla. So not that much. And also we want to round this to 2 sig figs because we have 2 sig figs on this number. So 2.1 10 to the minus 4 Tesla. That's how strong the magnetic field is inside the wire, half a millimeter away from the center. Okay, next, we're going to have R equal to 4.50 millimeters. And of course, now we're outside of the wire because this is bigger than the radius of the wire. And that means the formula for magnetic field that's relevant is mu naught times I divided by 2 pi times R. So what does that look like? We have, again, 4 pi 10 to the minus 7. For mu naught, we have 2.338 for the current. On the bottom, we have 2 pi. And we need to put in this number, which tells us how far from the center we are. 4.50 millimeters, or 10 to the minus 3 meters. Here's what this works out to. This is 1.039 10 to the minus 4. Is that right? Yeah, 10 to the minus 4. Now in this case, we'd want to keep 3 significant figures. So let's write the final result down here. We have 1.04 times 10 to the minus 4 Tesla. So that's how strong the magnetic field is when we're at this point outside.
Okay, so here's another conceptual example that we can look at. Consider a coaxial cable. So here's what a coaxial cable is, if you're not familiar with this. Basically, we have a cylindrical conductor whose radius is A, and that's surrounded by a cylindrical conducting shell. So the inner radius of that is B, and the outer radius is C. So we've got these two conductors, one is on the inside, the other's on the outside, and there's some space between them. So we typically fill that empty space, or the space between them, with some kind of insulating material between those two conductors. Now in a coaxial cable, the two conductors carry the same amount of current in terms of magnitude, but the current goes in opposite directions. Okay, so the inner conductor is going to be carrying a current going one way, and the outer conductor is going to be carrying a current going the other way. So I have a couple questions pertaining to this. What is the magnetic field at the center of the cable? So R is equal to 0. And then secondly, what is the magnetic field outside of the cable, where R is greater than C? So pause the video and try to use Ampere's law to work out these two questions, and then we'll go over it.
Okay, so this is not the prettiest picture I've ever drawn, but you can see what's going on here. We have the coaxial cable, so we're looking into it, we're looking at it face on, and this inner conductor here has a radius of A, and the current in this one is coming out of the page like this. Now this second conductor, the outer one, has an inner radius of B and an outer radius of C, and the current here is the same amount but going the other way. So the current I is going into the page right here. So the questions in this were about the magnetic field at various places within this coaxial cable. So let's start with R is equal to 0. Okay, now the way we're going to sort of figure out what the magnetic field looks like is just with Ampere's law. B dot dl is equal to mu naught times I enclosed. So here I'm going to draw a little Amperian loop. And the radius of this thing, if I can add that to my already kind of busy diagram, is R. And this is the path we would integrate over to figure out what the magnetic field looks like at any given point. Now we're asked here to consider the case where R is equal to 0. So that's like shrinking this path until it's got basically no size at all, and you're just right there at the middle, at the center of everything. Well, in this case, your I enclosed would be 0. Okay? If your path has no size, it's not enclosing any current. So right away, that's telling us that B is equal to 0 right at the center of that coaxial cable. Okay, the other case is, what if we're outside of the entire cable where R is greater than C? What then? Well, let's also think about I enclosed in this case. Okay, so now our Amperian loop is way out here. It's enclosing the entire coaxial cable, and we're enclosing the current that's going through this inner conductor. We're also enclosing the current that's going through this outer conductor. Now, both of those currents are I, and if they were going in the same direction, I would just add I plus I, but they're not. They're going in opposite directions, which means they cancel each other out. I'm not actually enclosing any current here either, which implies that the B field is 0, both at the very center and anywhere outside of the coaxial cable. And that's why a coaxial cable is very useful, because the magnetic field goes to 0 outside. That means even if you're running some current through this cable, it's not going to create a magnetic field that's going to interfere with other electronics nearby, because that magnetic field is going to 0 outside.
Okay, so here's another example. What we have here is a wire with a non-uniform current density. So what you're seeing here in the picture is an infinitely long conducting wire of radius capital R that has a non-uniform current density. So if it's non-uniform, it's not just some kind of number, it's actually a function. It depends on your radius. So J, the current density, is a function of R, and that's given below. So let's look at what it shows us. J as a function of R is equal to J naught times little r divided by big R. So in this expression you see here, J naught and big R are both constants. But little r isn't, right? That's your distance from the center. So what this is saying is, as you go out from the center of the wire, the current density gets bigger and bigger. That's what's happening here. So what we're going to do is use Ampere's law to find an expression for the magnetic field as a function of r. Again, that's our distance from the center of the wire. Okay, so how is this going to work? First, we're going to apply Ampere's law to this loop, which is, as you can see, inside of the wire. So the radius of that loop is less than the radius of the wire. And if we work out this using Ampere's law, let's see what we get.
All right, so here's what we're dealing with. We're looking into the wire. Once again, we're looking at it face on. And since we're trying to consider what the B field looks like when we're inside the wire, our Amperian loop is going to be this it's just a circle with a radius that's less than the radius of the wire. And we're going to apply Ampere's law. B dot dl equals mu naught times I enclosed. Now, there's one part of this that we've seen already how it works, so I'm just going to skip right to the result. What we have here is a cylindrically symmetric B field. This is what we always see when we're dealing with an infinitely long wire. B dot dl just turns out magnitude of B times 2 pi r. Okay? So that's the magnitude of the B field. That's the total distance around our loop. That's how it works out. On the other hand, I enclosed, in this case, is going to take a little bit of work because the current density is no longer uniform. Okay, so the current is not uniformly spread out throughout the wire. Instead, it's given by some kind of function. So what we have to do is think about current density in terms of the derivative di dA. Okay, and so di, some little infinitesimal amount of current, is equal to J, the current density, times dA, some kind of infinitesimal amount of area. All right, so I enclosed, that's going to be an integral of all these di's, right? If I add up all the infinitesimal bits of current that I'm enclosing, it include everything, then I have I enclosed. And that means for I enclosed, what we have is the integral of J dA. All right, so J is given to us in this problem. What about dA? How do we deal with that? Well, the way you want to think about dA is that a circular area is pi r squared. So the derivative of that area with respect to radius is 2 pi r. And that means dA is equal to 2 pi r times dr. That's what's going in there for dA. Now, what's going in here for J? Well, that's just the current density function that we were given. So let's put in what we were given. This is J naught times little r divided by big R. And dA is 2 pi little r times dr. Okay? And of course, we want to include all of this current we're enclosing, which means we have to go from 0 radius all the way out to little r like this. Now, if it's getting a little confusing how I have little r in the integration limits as well as here, we can call this r prime just to distinguish the two, if you want to do that. But here's what we're dealing with at the end of the day to find I enclosed. We've got constants, which are 2 pi, J naught, and big R. And then all that's left in the integral is 2 factors of R. So we'll call that r prime squared dr. All right, so how does this integrate? It's a simple power rule. R squared goes to 1/3 r cubed. So I have 2 pi J naught divided by big R. And then this goes to 1/3 times 1/3 times r prime cubed. Take that from the limits 0 to r. Okay, so I plug in the top limit, this just becomes r. I plug in the bottom limit, it becomes 0. So since the bottom limit is just 0, this overall integral works out to 2 pi times J naught times little r to the 3rd power divided by big R. So there we have it. All right, so what do we have so far? Let's just go back to Ampere's law. We know that B dot dl is going to work out to this because we have this certain type of symmetry that we've seen before. We know that I enclosed has worked out to this. Now let's just put everything together back in Ampere's law and then see what our final expression is. So I'm going to have to erase some of this stuff. So B dot dl is magnitude B times 2 pi r And I enclosed over here, we just came up with that expression, which was 2 pi j naught, little r to the third power divided by 3, times big R. Okay, there it is. So cancel out 2 pi. Cancel out this factor of r right here, just divide it, and now this becomes r squared over here. So the magnitude of B, when we're inside of the wire, is given by mu naught times j naught times little r squared divided by 3 times big R. So notice the magnetic field in the wire is increasing like r squared. When we had a uniform current density, this was just r to the first power. So you see how changing the current density in the wire changes what the magnetic field looks like inside that wire as well.
And so the answer is the magnetic field strength for this loop is equal to mu naught times j naught times little r squared divided by 3 times big R. Now, just keep in mind that everything in this expression is a constant except for little r. What is that telling us? Well, we have little r squared on top. It's telling us the magnetic field is increasing with distance from the center as r squared as long as we're inside of the wire. So the next thing we'll do is apply Ampere's law to this second loop, which is outside of the wire. So the radius of that loop is bigger now than the radius of the wire. And so let's work out using Ampere's law what the magnetic field looks like out here.
Okay, so now to work out what the field looks like when we're outside of the wire. So now our Amperian loop is a circle with a radius that's bigger than the radius of the wire, as shown here. And when we apply Ampere's law, that's B dot dl integrated over this loop is equal to mu naught times I enclosed by the loop. So just as before, we know exactly what B dot dl looks like. We have this cylindrically symmetric B field. It works out to magnitude B times 2 pi r. We've seen that before. And then I enclosed, well, I mean, one way I could think about I enclosed is I'm looking at the entire current in the wire, right? I'm outside of the wire, so this thing is enclosing all of the current that runs through it. So I could just say I enclosed is I total and then see what happens. Well, if we work that out, we have, so B dot dl becomes magnitude B times 2 pi r. And then we have equals mu naught times I enclosed, which is just the total current. All right, so what do we get here? We get the magnitude of B is equal to, divide out 2 pi r, mu naught times I total divided by 2 pi r. So basically, it just looks like any other wire as long as you're outside. It's given by mu naught I over 2 pi r. So there's another way we can think about this. Let's go back to our expression from the previous problem for I enclosed. And remember that what we came up with is 2 pi times j naught times r to the third, that was little r, divided by 3 times big R. But now if we're trying to say that the enclosed current is just the total current that runs through the wire, that means we should take this R and make it big R, because that way we're taking the total current all the way out to big R, which is the total current that's in the wire. Okay? Well, if we have big R to the third on top, and we have big R to the first power on the bottom, we can cancel that out. Now we have big R squared on the top. Okay? And just like before, we can plug everything we know into Ampere's law, where we have magnitude B times 2 pi r equal to mu naught times this total current, which over here we just said is 2 pi times j naught times big R squared divided by 3. And so first let's cancel out the 2 pi, and then let's divide out the little r, and it puts it down there. So another way we could write the B field outside of the wire is mu naught times J naught R squared divided by 3 times little r. Okay, so there it is.
And the result that we get is that the magnetic field strength is equal to mu naught times J naught times R squared divided by 3 times little r. So again, the only thing that is a variable that's not constant here is little r. So it looks like outside of this wire, the magnetic field decreases like 1 over r as you go further out. And we can actually rewrite this as mu naught times I total. That would just be the total current in the wire divided by 2 pi times little r. And if you notice, that expression right there is just our expression for the magnetic field from a thin wire. So what this is telling us is as long as we're outside of the wire, it just looks like what we're familiar with, the magnetic field from a thin wire. Okay, so the next thing we'll do is just try to see what this looks like when we plot the magnetic field as a function of radius, as a function of distance from the center. And so on the vertical axis, we have the strength of the magnetic field. On the horizontal axis, we have the radius or distance from the center of the wire. So as we saw, the B field increases when we're inside of the wire according to r squared. So what we're going to have, at least for the first part of this graph, is this concave up parabola. That's our r squared curve. But then, as soon as we go outside of the wire, so as soon as our radius gets bigger than capital R, now the magnetic field is falling off. It's getting smaller, like 1 divided by R. So that's really what we're seeing here in these graphs. Is just sort of a confirmation that the magnetic field increases as R squared inside of the wire and decreases as 1 over R when we're outside of the wire. That's what we found using Ampere's law. Okay, so we've done a few examples of infinitely long straight wires and how we can use Ampere's law to calculate the magnetic field in those sorts of situations. But there are other examples that we want to get to. So the next one is a solenoid. Okay, so if you haven't seen this before, this is what a solenoid is. It's just a current-carrying wire that's tightly wrapped around a cylinder many, many times. So that's what you're seeing in the diagram. It's just a wire. It's wrapped around a cylinder many, many times. What we want to know is what kind of magnetic field gets produced by this solenoid. Well, the first thing to remember is that magnetic field lines, they form loops around currents. And even if the current is sort of wrapped up in this complex shape, it's still true that the magnetic field lines are going to go in loops around the current. So let's actually follow one of those magnetic field lines. Okay, so just pick any one of these magnetic field lines on the diagram, and you'll see that it goes into the solenoid, so it's inside of that cylinder. Then it loops back around outside of the solenoid, and then back into it. So it forms this sort of closed loop. Now, inside of the cylinder, the lines are pretty tightly packed because every single field line has to go in through the cylinder at some point. But then outside of the cylinder, which is a much, much bigger volume for those lines to be in, they're really spread out because you have the same exact number of field lines in a much, much smaller volume. And remember that visually, the more tightly packed the field lines are, the stronger the magnetic field is, the bigger the magnitude of our magnetic field. So just visually, this is showing us that inside the solenoid, the magnetic field is much, much stronger than outside. And in particular, let's take a look at the example where, or let's take a look at the case where the diameter of the solenoid, so the diameter of that cylinder there, is very, very small compared to its length. Okay? In that case, the field lines inside the solenoid are going to be incredibly tightly packed, and outside of the solenoid, the field lines are going to be incredibly spaced out. Okay? So essentially, what we'll have is inside the solenoid, a really strong magnetic field that's basically uniform It's all kind of pointing in the same direction with the same strength everywhere inside. And then everywhere outside, the magnetic field is so small that we can essentially ignore it. In the limit where the solenoid becomes infinitely long, the magnetic field outside actually goes to zero. So that's what we'll be really considering, is this sort of ideal solenoid that's infinitely long. The magnetic field inside is nice and uniform. The magnetic field outside is going to zero. That's what we're dealing with the solenoid. Okay, so the next step here is to see how we can use Ampere's law to solve for the magnetic field inside of a solenoid. And again, we're thinking of a solenoid in this sort of idealized picture as being infinitely long, where there's no magnetic field outside and a uniform magnetic field inside. What you see in the diagram here is a cross-section of the solenoid. So you can see the magnetic field lines are going to the right. On the top of the picture, we see the wires that are carrying the current going towards us, so out of the page. On the bottom of the picture, you see the wires that are carrying a current going into the page. Okay, so that's what's being shown here. So as far as the variables go, the current in that wire, we're going to call that I. And again, this wire is wrapped very tightly around the cylinder. So if we want to specify how tightly is the wire wound around the cylinder, we're going to use this variable lowercase n, which is the number of turns of wire per unit length. So lowercase n is uppercase N, that's how many times we've wrapped this around the cylinder, divided by L, that's the length. So again, we're going to find the magnetic field inside of the solenoid using Ampere's law. And so what that means is we need to pick an Amperian loop to do our calculation. So let me show you on this diagram which Amperian loop we're choosing. This is a rectangle. The dimensions of the rectangle are L by W, and it has 4 sides to it. So let's see. The side labeled 1, that's inside of the solenoid. It's just going in the direction of the magnetic field. The side labeled 2, that's taking us out of the solenoid, and the direction is perpendicular to the B field. The side labeled 3, now we're completely outside of the solenoid, so just follow that path going to the left. And then finally, what's labeled as 4, that takes us back into the solenoid to where we started. Now we have a complete loop. It's a closed loop. So now let's work out, using Ampere's law, what this gives us for the magnetic field.
Okay, so now to use Ampere's law to figure out what the B field inside of a solenoid looks like. Again, this is our Amperian loop. It's this rectangle where we have sides 1, 2, 3, and 4. And since Ampere's law states that B dot dl is equal to mu naught times I enclosed, we better get a handle on both sides of the equation. I might want to know what B dot dl is for this entire loop. So let's think about it. B dot dl for the entire loop can be broken into these 4 parts. We have B dot dl for the first path, that's this one, as well as for the second path, and then the third and the fourth path. Okay, that looks like a lot, but most of these are going to 0, and I'll show you why. Okay, so we have B dot dl 1, 2, 3, and 4. How about we start with this? Path number 3. So up here, we're in the solenoid. So there's this B field, and we'd like to know what it is. But outside, where path 3 is, the B field is equal to 0. That's the assumption. If we have an infinitely long solenoid, this B field outside is actually going to 0. So I can cross this out, because if I have no B field, then the integral over that B field is certainly going to be 0. Okay, let's also look at path 2, where part of it is inside of the solenoid. So there is a B field here, but we're taking the path going exactly perpendicular to the B field. Okay, so B dot dl, if you're going perpendicular to the B field, is going to be 0 as well. And then as soon as we get outside, then there's no B field. So the point is the integral for that entire second path is going to be 0. As far as the fourth path here, the one that goes starts here and then goes back into the solenoid, well, that's 0 for the same exact reason, right? There's no B field here, so we're definitely getting 0 for the integral. And then up here, we're going perpendicular to the B field lines, which guarantees that the integral b dot dl goes to 0. So the only part of this we have to think about is the first part, b dot dl1. So like any other dot product, the way we want to treat this is the magnitude of the first vector, b, magnitude of the second vector, that's dl1, and then cosine of the angle between them. But notice how my path and my B field are both going straight to the right, so there's no angle, there's 0 degrees between them. And okay, cosine of 0 goes to 1. The magnitude is a constant which we can pull out, and then I just integrate all my dl's. Okay, so what happens when I add up all these little bits of length from here to here? Well, that's just the total length, so we'll call it L. Okay, so the total length of the path from here to here, we're just calling that L. What about I enclosed? So we have all these different turns of wire that we see right here, and we're enclosing all of them. So each one of them carries a current I, but we're not just enclosing one of those currents, we're enclosing a whole bunch of them. I don't know what exactly that number is. I'm showing some number here, but the point is the number of those wires we're enclosing, let's call that N, times I, which is the current that each one has, is going to give me the total current that I'm enclosing in all of these wire segments right here. That's the idea. Okay, so I'm going to take everything together. We're going to put it all together in Ampere's law. B dot dl, that integral goes to magnitude B times this length L right here. Then we have that equal to mu naught times I enclosed, and I enclosed is N times I. So we're almost done. To solve for B, what we have is mu naught times capital N, and then we have to divide out this L, so put it down here, times I. So therefore, if you remember, that lowercase n is the number of turns of wire per unit length. We can re-express this as mu naught times lowercase n times I. So that's what the B field in a solenoid depends on. It depends on mu naught. It depends on the number of turns per unit length of wire. And it also depends on what current.
Okay, so here's what we found, that the magnetic field is equal to mu naught times lowercase n times I. So that's the strength of the magnetic field inside of a solenoid. That's the formula for it. And with that said, let's do a little calculation with that formula. Let's say that you're trying to design a solenoid that produces a 1.50 times 10 to the minus 3 Tesla magnetic field when we have a 2.5 amp current running through the wire. If the solenoid is completely empty, it just has empty space inside of it, and mu naught, the permeability of free space, is 4 pi times 10 to the minus 7 Tesla meters per amps, how many turns of wire per meter will be required? So that's asking you to solve for lowercase n, the number of turns per unit length. The second question is, if the neighboring turns of wire are touching, what should the diameter of the wire be in units of millimeters? So what I want you to do is pause the video, work this out using the equation we derived, and see if you can get the right answer. Then we'll go through it.
All right, so let's start with the formula that we derived using Ampere's law for the magnetic field strength inside of a solenoid. And that was that the magnitude of B is equal to mu naught times lowercase n times I. Now here, what we're going to do is solve for lowercase n. That's the number of turns of wire per unit length along the solenoid. So n is equal to the magnetic field B divided by mu naught times I. Let's work that out. So in this case, we're trying to design a solenoid that has a magnetic field strength of 1.50 times 10 to the minus 3 Tesla. Okay, and then down here, we have 4 pi times 10 to the minus 7 Tesla times meters per amps. That's the constant mu naught, the permeability of free space. And then finally, we have 2.50, is that right? Yeah, 2.50 amps. That's the current that we want to run through this thing. Okay. So if you look at the units that come out of this, you see that Tesla cancel out, and so do amps. And it looks like on the bottom we're left with meters. So we could consider the units here to be inverse meters. And the number we get is 477.46. We'd round that to a nice 3 sig figs. And the way to interpret this is 477 rounded off turns per meter. Okay, so that's how many times we have to wrap this thing around the solenoid per meter to get this to work. And so to get the second part of this, what I want you to think about is take that answer we just found, and what if we invert it? Okay, so what if I took 1 over 477.46, and again, that's turns per meter. But if I invert that, flip the units around, and now we have meters per turn. And the number here works out to something pretty small. It's 0.00209 meters per turn. And how do we interpret that? Well, first, let's put it into a more sensible unit. So 0.00209 is the same as 2.09 millimeters for every turn. Okay? And if we think about what the neighboring turns of wire look like if they're all touching, in other words, if there's no space between them, we have something like this. Okay, and so right here is the diameter of one of those turns of wire. Well, if there are 2.00 millimeters per turn, and there's no empty space between the wires, then that's also just the diameter. The diameter of the wires is 2.09 millimeters. Okay, so if we want to design the solenoid so that it has a certain magnetic field strength, 1.5 10 to the minus 3 Tesla on the inside, then we need this many turns per meter. But then if we want all the turns of wire to be touching so there's no empty space between them, then the diameter of that wire should be 2.09 millimeters. That's what we found.
As far as Ampere's law goes, we've touched on 2 basic symmetries. One is an infinitely long straight wire, and the other is an infinitely long solenoid. And so we have 2 more to do. The next one is called a toroid. So remember, I showed you this previously. A toroid is basically a donut shape where we've wrapped a wire around that donut shape many, many times. And the easiest way to think about a toroid is you can get a toroid by taking a solenoid, okay? That's just a straight cylinder with a bunch of wire wrapped around it. If you bend that solenoid so that it loops back in on itself, you get a toroid. Okay, so basically a toroid is a solenoid that's bent into a circular shape. So it's not really too different from how we deal with a solenoid if you think of it that way. Because what's going on inside of the toroid, you have a B field, and outside of the toroid you have a pretty much negligibly small B field. We can pretty much ignore the B field outside, just like with the solenoid. So what you're seeing in the picture here, again, is a cross-section of the toroid. Okay, so imagine sort of cutting the toroid in half. This is what we would see. You would see the B field lines going around the toroid rather than being just straight. Now they're sort of looping around the toroid, forming a circle. And on the left side, you see the current in those wires that's coming out of the page. And on the right side, you see that same current looping back going into the page. All right, so what are some of the variables here? The current is I, and then uppercase N is going to be the total number of turns of wire. So the total number of times that this wire is wrapped around the toroid. So we're going to use Ampere's law once again to figure out what the B field inside of this toroid is. So here is our Amperian loop. I'm actually only showing part of it because we're only seeing part of the toroid in this picture. But let the Amperian loop be a circle of radius r that goes all the way around the toroid. So it is a closed loop. And so what we're going to do here is go ahead and use Ampere's law to get the B field in this situation.
All right, so now to figure out what the magnetic field inside of this toroid looks like, we're going to have Ampere's law, integral over our closed loop, B dot dl, is equal to mu naught times I enclosed. All right, so here's what we need to think about. What's B dot dl? Let's start with that. Well, if you recall, our Amperian loop is a circle which goes all the way around the toroid, and the radius is r. Notice that our magnetic field lines were going in that same direction as our dl vector. So we're dealing with a situation where B dot dl gives us magnitude B, magnitude dl, and these two vectors are going in the same direction. So we have cosine 0, which is 1. Okay, next, we take out the magnetic field strength B from the integral because it's going to be completely uniform all around this toroid. And then what we take is the integral of dl all around our loop. So again, this is just adding up all the little bits of distance if we go around the loop. But when we complete the loop, we have a circle. So that distance is 2 pi r. So when you have a circular Amperian loop, this is what it's going to look like. You've got the magnitude of B times 2 pi r, which is total distance around the loop. Okay, I enclosed, that's the next part of this. So the way we want to sort of think about I enclosed is how many turns of wire, okay, the number of turns of wire, how many of those do we have that we're enclosing? And then if we multiply that by how much current is in each wire, or in each turn of wire, then we have the total current we're enclosing. Okay, so we have to account for the fact that we're enclosing the current in all those different turns of wire in our Amperian loop. And so that's actually a fairly big number. So what we have is N, that's the number of turns of wire. I, that's the current in each one of them. So that's what we're doing here. Okay, finally, we're going to take B dot dl, set that integral equal to mu naught times I enclosed, and we'll get our answer. So B dot dl was magnitude B times 2 pi r, and that's equal to mu naught times I enclosed, which is the number of turns times the current I. That tells us that our magnetic field strength B is equal to, we've got mu naught times N times I. That's on top here. On the bottom, we have 2 pi r. So I actually just want to point something out about this formula here. Notice how the number N comes into it. So the more times we wrap the wire around the toroid, the bigger N is, then the stronger the magnetic field we can have. So we can actually get a stronger magnetic field by sort of coiling the wire into a tighter and tighter space. That's the idea.
And here's what we found, that the B field is equal to mu naught times N times I divided by 2 pi r. So that's how it works for a toroid. The last one we want to do here is an infinite current sheet. So again, think of a plane that carries current, and the plane is infinitely large in terms of its area. One way we can think about a current sheet is just a bunch of wires that are packed tightly together to form an infinitely long sheet. Okay, so what you're seeing here in this picture is the current sheet viewed edge on. So we're looking into the current right here. As you can see, the current is coming out of the page at us. We're only seeing a small, portion of the overall sheet because it's infinite, but there it is. Okay, so if we have a bunch of wires that are packed tightly together, and each one of them carries a current, let's call it I, and we'll let lowercase n be the number of wires per unit length. So in other words, lowercase n is capital N divided by L. That's the number of wires per unit length. Okay, so one thing this picture is missing is a sketch of what the B field lines look like. So what direction is my magnetic field going in this situation? So to work this out, I want you guys to think about the right-hand rule. You see that the current in this case is coming out of the page. So the right-hand rule says if you take your thumb and you point that in the direction of the current, then your fingers will be pointing in the direction of the magnetic field. So take your thumb, point it out of the page, and make sure your fingers are up, so they're in the upper portion of this picture above where the wires are. Okay, you're going to see that the fingers of your right hand are pointing to the left. Okay, so now put your fingers down so they're below the wires in the lower portion of the page. Now your fingers should be pointing to the right. Okay, so in other words, the magnetic field is going to the left above the wires, and it's going to the right below the wires. That's what we can figure out just by using the right-hand rule. Okay, the next thing is, if we're going to apply Ampere's law to this situation, we need to choose some kind of loop to work with. Now in this case, my Amperian loop is going to be another rectangle. The dimensions are L by W, and we have 4 different sides. So here, let's go through it. Side 1, that's on the top of the diagram. That's just going along the magnetic field to the left. Then we go down to side number 2. That's going perpendicular to the magnetic field. It's just taking us across the current sheet. Side number 3, that's on the lower portion of the diagram. It's going across the magnetic field. And then finally, side number 4, that's on the left. That's taking us back the other way across the current sheet. So again, we have a closed loop. We can apply Ampere's law to this and figure out how strong that magnetic field is due to this current sheet.
So actually, in this example, the first thing I want to do is sort of motivate why it is that I know the magnetic field looks the way I showed you on the slide. Okay, so here we're going to make kind of an argument from symmetry. Okay, we've got the current sheet, which we're thinking of as a bunch of wires stacked together end to end like this. It goes infinitely far in either direction, so I'm only showing you, a small part of it. But what if we take a look at a point up here above the current sheet, which is an equal distance away from this wire? Let's call that 1. And this wire, let's call that 2. All right, so if I think about the magnetic field from wire number 1, well, a wire, if it's carrying a current going out of the page like this, take the thumb of your right hand, point it out of the page, and then your fingers will be curling in the direction of that B field. So it's kind of up and to the left like this. That would be what we'll call B1. Okay? Now, there's also a magnetic field from this wire, which is number 2. The current's also out of the page, so if you want to know what the B field looks like, just take your thumb, point it out of the page, and your fingers will be curling around in the direction of that B field, which is sort of down and to the left as well. So by symmetry, we can see that the vertical components of B1 and B2 are going to cancel out, leaving us with a magnetic field that's just going to the left. Okay, so because we have this infinite plane with infinite wires going in either direction, the vertical components of your B field are just going to cancel out in pairs like this. Okay, so for any B field that has a component going up, I have another B field that has a component going down, and they just cancel out. So all you're left with is the B field going to the left. You can make a similar argument down here to show that the B field is going to the right. So that's how we know it looks like. All right, so here we have our infinite current sheet that's carrying a current coming out of the page. We're looking at this current sheet edge on, so that's what it looks like. And this is our Amperian loop. It's a big rectangle where we have side 1, side 2, side 3, and side 4. We're going to apply Ampere's law to this, and what we're going to get is some kind of expression for the magnetic field that you see here. Ampere's law, B dot dl, integrated over this loop, is equal to mu naught times I enclosed. That's how it works. So let's first think about B dot dl for the loop that we've drawn. So kind of similar to what we saw with the solenoid, we have these 4 parts. We need to add B dot dl for each one of those parts individually. So we'll have B dot dl1, we'll have B dot dl2, okay, we'll have B dot dl3, and then finally B dot dl4. 4 integrals. Now some of these we can immediately argue are going to go to 0. So in particular, I want to think about number 2. Notice this path is going straight down, whereas my B field is down here going to the right and up here going straight to the left. So this path is perpendicular to the B field. That means the B dot dl, that dot product, is going to 0. In a similar way, path number 4, it's going straight up like this. It's also perpendicular to our B field, so that should be 0. When you take the cross product of perpendicular vectors, you're always going to get 0. Okay, now let's work out the remainder. We've got B dot dl1. So this is the integral where we have the magnitude of B, okay, magnitude of dl1. And if we look at path 1, it's going in the exact same direction as our B field. So we're going to have cosine 0. Okay, and then over here, if we look at the third path, we have something similar going on where you have the magnitude of B, the magnitude of dl3, and this third little piece of the path is going exactly in the same direction as the B field. So again, we have cosine of 0. Okay, so we're getting somewhere. To continue on this work over here, first we can pull out the B field strength from this integral because it's going to be uniform all over the path. And then we can take integral of dl1 is what we're left with inside, because cosine of 0 goes to 1. Over here, pull out the b, and then we have the integral of dl3. Okay, so look at this path up here, that's path 1, and look at this path down here, that's path 3. They have the same exact total length, okay? And if we look at the integral of dl along, let's say, path 1, well, that's just adding up all the little bits of distance along the path. When we integrate all those distances together, we're getting the total length. So we're just getting L. Okay? And the same thing goes here. We're just getting this total length let's call that L. So we're getting two terms that are just magnitude B times L, and they're added together. So we get 2 times the magnitude of B times L. Okay? How do we think about the enclosed current? Well, this path encloses a whole bunch of different wires. Let's say that number is N, and each wire is carrying a current I. So if we take the number of turns of wire that we're enclosing here times the current each one has, that's going to give us the total current that we're enclosing with our loop. That's the idea. Okay, so to finish this off, let's take what we know. So I'm going to erase some of this and just plug it into Ampere's law. Okay, so these two results here. Ampere's law says if we take B dot dl, which right here we found is 2 times the magnitude of B times this length right here, that should equal mu naught times I enclosed, which is N times I. So for the magnitude of this B field, just divide out 2 times L. And so what we're going to have is a half out front. We're going to have mu naught, and then N divided by L times that current. So the last thing to do here is to realize that N divided by L, that's the number of turns per unit length. That's what we call lowercase n. So we'll have 1/2 times mu naught times lowercase n times I. That's the answer. That's the B field from an infinite current.
And what we'll find is, when you do the calculation, that B is equal to 1/2 times mu naught times lowercase n times I. So now we've covered all of the different types of Ampere's law problems, right? We've got straight wires, we've got solenoids, we've got toroids, and now we've got infinite current sheets. And that's really it. Those are the only examples we're going to see. So there it is. So the next thing we'll do is an introduction to the Biot-Savart law. We'll talk about this a lot more in the next part of the lecture, but we'll just do a quick introduction to it right here. Okay, so here's the introduction. Remember all the way back at the beginning of the semester when we were calculating electric fields, and there was this sort of brute force method we took where we broke down some kind of object into little infinitesimal pieces, little dqs, the little charge elements, and each one has an electric field that it contributes given by Coulomb's law. Remember that the electric field dE is k dq over r squared. Then, if we know what kind of electric field each individual charge is contributing, if we integrate over all of those, then we get the total electric field. So I call that the brute force method because it gets a little ugly sometimes in terms of the integrals, but it will get the job done. On the other hand, we had a simpler method, okay, which was Gauss's law. And conceptually, it's a little trickier, but some of the math is a lot easier when you're using Gauss's law. Remember what Gauss's law said. It said that E dot dA integrated over a closed surface is equal to Q enclosed divided by epsilon naught. So we were able to use both of these methods, Coulomb's law and Gauss's law, to calculate an electric field. But remember that Gauss's law was only really useful when we had a high degree of symmetry. So we could do it for spheres, we could do it for cylinders, we could do it for infinite planes, but that was about it, right? Only in these special cases. Now, when it comes to calculating B fields, we're in a similar situation where we've learned about Ampere's law, the fact that B dot dl integrated over a closed loop is equal to mu naught times I enclosed. You can use that to calculate a B field as long as you have a certain type of symmetry. If you have an infinite wire or a solenoid or things like that, we can use Ampere's law. But there's another method. It's called the Biot-Savart law, which is pretty similar to Coulomb's law. It involves breaking your currents into little infinitesimal pieces, and then integrating over all of those to get the total magnetic field. That's what we're going to learn about next time. That's what the equation in the bottom left of the screen shows us. That's the Biot-Savart law. So next time we're going to get into how to use this and what it means. So that's it for today. I just want to say to everyone, stay safe, stay healthy out there. I'll see you in the next lecture.